So the last class we talked about batteries kind of being like capacitors and using their chemical reactions to step up the energy of ions within that battery or like within the electrolyte solution, right? We also talked about how this increases the electric potential energy of those ions. And then if you connect batteries in series, you can just add up the voltages. So if I have three 1.5 volt batteries, well then I just add up the voltages to find that I've got a total voltage difference of 4.5 volts. Last but not least, we talked about not all resistors are created equal, or not all wires are created equal. Right? The current through a wire depends on not only the voltage difference that I put into it, but the resistance of that wire. And the resistance of that wire can be found by by the length of that wire divided by the cross-sectional area and the resistivity of that material, which you can find on page 721. And last time we also introduced the idea of resistance and resistivity along with Ohm's law down here. That the current in a wire is equal to the voltage difference across the battery divided by the resistance of the material that it's going through. And depending on the material that it's going through, we can calculate the resistance. And so last time you kind of just did some plug and chug formulas of Ohm's law with voltage and current and resistance. And we didn't really talk about too much what it was exactly. Ohm's law is the basis of circuits and building circuits and electricity. It's used by electricians, auto tech, stereo installers. Our aviation maintenance has an entire unit on Ohm's law where they practice it over and over and over again with relation to keeping up with airplane electronics. And it is, again, just so you know, this is Ohm's law. We can also write it as delta V equals I R, and this is actually the way that I write it, just because it's easier for me to remember. And so I want to take a minute and just kind of talk about this. And so voltage is the push or the pressure behind the current, right? A greater voltage difference is going to usually lead to a bigger current. Not always, but usually, right? And so if I have something really fun that I got for Christmas, maybe it takes a lot of batteries because there are many circuits in it. While if you just have something simple like a remote, it's just basically got a couple of functions, you might only have 2 batteries in that, right? It doesn't require as much current to operate that device. And so the voltage difference, or in the batteries, what we're talking about is the EMF. The EMF of a battery is just equal to the voltage difference across a battery. So when you see that, right, know that that's all that is. It's just voltage for a battery. That's the push behind the current. The current then refers to the quantity or volume of electric flow. And remember, the current, is equal to the change in charge passing a point at a given time as well. So we can not only think about current in terms of Ohm's law, we can think about it in terms of charges flowing past something, right? And the current flowing through something is completely dependent on what it's able to flow through. And so the thickness of the wire, what the wire is made of, the resistivity of the wire, all of that is going to affect the current that's able to flow through. And then last but not least, resistance is the pushiness against that flow. And so if we have wires have a resistance, we're going to model them as not having resistance. Those are called ideal wires. But if we talk about things like light bulbs, this is the symbol for a light bulb, or a resistor of some kind, maybe that's not a light bulb, maybe it's something that makes a noise, or something that has a motion, maybe like a fan. Anything that uses electricity is in turn a resistor. And so as you look around at maybe your cell phone and your computer, maybe you even have a fan going in the room, all of those things are resistors, and they kind of use or require a current for them to operate. And so just a little bit of a review, right? For voltage, we can talk about it as the EMF of a battery, which is this funny little E, or we can talk about it as a delta V if we're talking about household circuits. The change in voltage is 120 volts. So that's what you plug into a wall with. We also have current, which is represented by the symbol I, measured in amps, and then resistance R, which is measured in ohms, right? And so, again, these unit abbreviations, and then the symbols that we're using in our formulas for those values. There's a couple of general rules and a couple of ways that circuits work. One of those ways is that the resistance in a circuit doesn't change. And so if the resistance is not changing, if I increase the voltage difference, then the current also increases in that circuit. If I decrease the voltage supply, well then current also decreases. And then our second situation is that sometimes voltage is the thing that doesn't change, right? Like out of a wall socket, it's always 120 volts, right? Or out of one AA battery, it's always 1.5 volts. So sometimes the voltage doesn't change. In this case, if I increase the resistance, well then the current decreases. And if I decrease the resistance, the current increases. And that makes sense. Like if I could decrease the pushiness against the current, well then the current can flow freely. The last kind of caveat to this is that there are ohmic and non-ohmic materials. While electricians and auto techs and our folks over in aviation maintenance spend a long time on this ohmic versus non-ohmic materials, I'm going to summarize and know that it's a generalization. So there are things that we describe as ohmic. They follow Ohm's law. And then there are things that we describe as non-ohmic. They don't follow Ohm's law. For the things that do follow Ohm's law, there's a linear relationship between the current, and the voltage difference required, right? And so if one goes up, the other goes up. This works for most resistors, and it works for metal wires, which is great. When we talk about current and circuits, this is really all we're going to focus on. However, I want you to know there's a lot of things in our lives and a lot of things that we're going to talk about and treat in this special way that don't necessarily apply, right? And so notably, non-ohmic devices are batteries and capacitors. The very things that we've built your foundation of electrical knowledge on actually don't follow Ohm's law. All right, and that's okay. I'm not gonna go too far beyond that, because what we're working towards is our household devices. And so for our household devices, the voltage difference is 120 volts. That's what comes out of your wall every single time, right? And I think, yeah, those look like that. So out of your home device, you get 120 volts. So I want to think about a toaster for a second. I eat toast every morning for breakfast, and I am very thankful for the resistance of these wires. So I have a constant 120 volts coming out of the wall as I plug my toaster in, and as the nichrome heats up, the resistance increases. And remember, heat was one of the signs of electrical current flowing through something. And toasters are really interesting because as they heat up, well, the resistance increases and increases and increases until ultimately it flips a breaker and it stops it and your toast pops up, right? And so you can actually kind of set the resistance with a timer on that. They heat up, they heat up, they heat up, and then they flip a little breaker within the toaster. It turns off and it pops your toast up. So as this nichrome is heating up and the resistance is going up, if my voltage is constant, what's happening to the current? Well, according to Ohm's law, that V is equal to IR, if my voltage is constant and my resistance is going up, well then my current has to go down. And what happens to the voltage difference? Well, the voltage difference is the same. It's still 120 volts. right? And so I want you to just take a second and work with Ohm's law, that delta V is equal to IR. Go ahead and pause the video and solve this one out. If I have a 12-volt battery and a 2 ohm resistor, what is the current flowing through that? Well, okay, I'll plug in. I've got 12 volts, and I don't know the current. And then I've got a 2 ohm resistor. I'm going to need to divide by 2 to find out that I've got a current of 6 amps. Okay. Going on, if I have a 12-volt battery and a current of 4 amps, well then, what is the resistance of my resistor in ohms? So again, delta V is equal to IR. 12 is equal to 4 amps times X ohms. I'm going to need to divide by 4 to find out that the resistance is 3 ohms. Right, so I've got a 3 ohm resistor. I also want to take a second and talk about the voltage across a resistor. I know that there's a voltage difference in my battery or my wall socket or whatever the case is. And I know that current is never created or destroyed, and because of that, what I need is a voltage drop. And so if I have like a battery and it's connected in a circuit to, let's say, a light bulb, if my battery is 9 volts, well then that means my battery steps up the electric potential 9 volts. And that means my resistor is also going to kind of take away from that voltage to let it start over at 0 when it gets back to that negative terminal of the battery. And so what I see is that the voltage drop across a resistor is equal to the voltage of either the wall or the battery. And so we could also talk about delta V being equal to the EMF of the battery. From this point on, unless specifically we talk about the resistance of the wires or the length and the composition of the wires, we're going to assume ideal wires, which means that there is no resistance in the wires and thus no voltage drop. We're going to assume that all the voltage difference happens across the resistor and not in the wires. And I'm going to go ahead and tell you this is a really big assumption. Things don't actually work this way. But for us to understand electrics and circuits, we're going to pretend that they do, right? So we're going to make this big assumption here. Resistors, or the resistance of a resistor, is actually marked on the resistor. And so while we're going to be drawing a lot of circuits, resistors are this little squiggly line, I also want you to have a context for what resistors actually look like. And so all of these guys in a circuit board are resistors, and all they do is control the current flowing to one of our electrical devices, right? And they are coded with these little bands on them. And there's a code that if you're in auto tech or aviation maintenance, those little bands tell you the resistance in ohms of that resistor. It's just a quick and dirty way to figure out the resistance and what's going through your circuit. Inside of a resistor, there is actually an electric field. And that electric field is equal to the voltage drop across the resistor divided by the length of that resistor. And so if I have a really big voltage drop across a really big length, well then my electric field is not that strong. But if I have a really big voltage drop across a very small resistor, then the electric field in that resistor is very, very strong. Right? So why the heck do we need resistors? Well, resistors are really good to decrease or increase the amount of voltage that's applied to a component in a circuit. And so, for instance, in your cell phone, you've got little tiny resistors that can help you control the brightness of your screen as you wish, right? There are thermoresistors, which vary with temperature, and there are photoresistors that vary with light. A really good example of your photoresistor is if you've ever lived in a place where you keep like a nightlight in the bathroom. It's got that little light sensor, and if it senses light, then that resistor kind of clicks on and decreases the current flowing to that light bulb. But if it senses a dark situation, that resistor will kind of flip off and vary the resistance to allow light to come to that light bulb and allow current to flow. Thermoresistors, same thing. If the temperature gets too hot, they kick on and stop the flow of electricity to keep that device from overheating. And again, in the real world, the value of a resistor is marked using color bands on that. And so we're getting to a place where we're talking about current, we're talking about resistors, and we're getting more realistic with our concepts of electricity. And at this point, it's time to review power, because so many things that you're aware of, like maybe your electric bill, if you've got one, is measured in kilowatt hours. And as you might remember, and if you don't, you're going to soon, watts is a measure of power. Or maybe you think of like a 60-watt light bulb. That's a description of how much power that thing uses, not of the resistance, right? So a quick review of power. Power is a measure of how fast work gets done. Power in the most traditional sense is equal to work divided by time. And in our case, work is going to be the change in electrical energy. And so what we see is that when we're talking about electrics, we're actually talking about the change in electric potential energy over time, over how quickly that happens, right? A charge is able to gain energy across a voltage difference, right? Like in a battery. And if I have a charge and I take it from one voltage to another, it either gains or loses energy depending on which way I'm moving. I can also talk about delta V for a battery being the EMF of that battery. And so when we talk about power in a circuit, or P, power, we can talk about the change in charge times the EMF divided by the time, or these are the more common ones. We can talk about current times the EMF of the battery, or current times the voltage difference. And again, if we're working in a house, it's 120 volts is what's coming out of that socket. So we can talk about the power provided by sources, right? And so knowing those formulas, I want you to just take a second, pause the video, and try and solve this on your own. Suppose a 60-watt light bulb and a 1500-watt heater are connected to a standard household 120-volt sockets. Which device draws more current? All right, and so I'm going to think about that formula, that power is equal to current times the voltage difference. And I'll have, let's say I'm going to do my light bulb work here and my heater work right here. So I've got a 60-watt light bulb, and it's plugged into a wall. That's 120 volts. And then I've got a 1500-watt heater. Whoop, and that too is plugged into 120 volts. And so if I divide by 120, I need to do that on both sides of both equations. What I find is that the light bulb uses much less current than a heater. And this is explained like when you plug in a heater or something big, right? Something that uses a lot of power, like maybe a vacuum cleaner or a heater. When you plug those things in, other things tend to dim immediately thereafter. And that's because these devices that use so much power actually kind of suck the current out of the circuit temporarily until it's evenly distributed once again. Right. I'm also going to give you a little bit of vocabulary. This word load is any electric load on a circuit that does work. And so shorthand, this is anything you plug in. You plug in. So anything that you plug in does work. That's our only purpose for plugging things into a wall, that these things do work in some capacity. If it does work, then it has power. And if it has power, then it's a resistor. And I'm going to repeat that again. So if it does work, then it has power. And if it has power, then it is also a resistor. And so what you're looking at right here is a connection of three variables: work, power, and resistance, or resistor. Great examples of all of these would be power windows, light bulbs, and motors. Power windows and motors tend to take electrical potential energy and change it to kinetic energy, while light bulbs change that to light energy. There's plenty of things that make sound energy out of electric energy, and so on and so forth. Right. Last but not least, I want to talk about batteries, resistors, and powers. So the power of a battery is equal to the EMF of the battery times the current. And the power of a battery is also equal to the power of a resistor. Resistors must obey Ohm's law so that we can substitute for power in our calculations. So what we wind up with is that the power of a resistor is actually equal to the voltage distance the voltage difference across that resistor squared divided by the resistance. And so know that power is ultimately pretty closely related to Ohm's law. All right, and that leads us to your homework. Forget about this part. I will be giving you a quiz on Friday, and I want to see you try at least 5 of these problems by Wednesday in class. And so Wednesday in class, you guys are going to share one of the problems that you're very confident about. You need to try at least 5 of them, right? Try at least 5 of them. Then they can be any 5 of these, and we'll go through your examples. You are responsible for teaching one of these on Wednesday, and whatever you guys don't cover, I will help you cover the rest. And I'll see you Wednesday in class.